Okay, 10a, for events A and B, it is given that the probability of B is 0.4 and the probability of A given not B is 0.15. Find the probability of A union B. So A union B is A or B. So I'm going to do this in a slightly different way. I'm going to do this as a tree diagram. And you've probably not seen this before, but you know, what the heck, let's try it out anyway. So either B happens or it doesn't happen. And then either A happens or it doesn't happen. And I know the chance of B happening is 0.4, so the chance of not B is 0.6. And I know the chance of A given not B is 0.15, so that means that this one is 0.85, right? So what's the chance of, and I don't have any information about these branches up here. So what's the probability that A or B happens? Well, actually, that's the probability that B happens. And if B happens, I don't care whether A or not A happens afterwards. B's happened, so A or B has definitely happened. So this is going to be 0.4 from this branch, plus the chance that if B didn't happen, then at least A happened. So 0.6 times 0.15, this comes out to be 0.49, which is the correct answer. Part B. In the last stage of a variety game show, the contestant aims to open a treasure chest containing the grand prize. The chest can only be opened when its two locks are unlocked. Each lock requires a unique key to be unlocked. The contestant is given up to 3 rounds to select the 2 correct keys amongst 6 different keys on the tray. For each round, he can only select one key, which will be tried on both locks. The selected key of a particular round will be removed from the tray after that round. Show that the probability that a contestant wins the grand prize in the second round is 1 upon 15. So show that the chance of him winning is 1 upon 15. So the probability of winning in second round, well, what's that going to be? Well, there are 2 locks, there are 6 keys, so that means in the first round he picks the key to one of the locks, so there's 2 of them, and there are 6 locks, 6 keys, so he's got a 2 upon 6 chance of getting the right key. And then the second round he's got a 1 upon 5 chance, assume he got it correct in the second round, so that comes out to be 1 upon 15. So that's where that number comes from. Part 1. Find the probability that the grand prize is 1 and the contestant selects the correct key in the first round. Okay, so if we want to find the probability that he wins and correct in round 1, what's that going to be? Well, that's the probability he is correct in round 1 and correct in round 2. Oops. Or the mutually exclusive event that he was correct in round 1 and correct in round 3, and presumably incorrect in round 2 if it went on to round 3. So what does that mean? That means that if he's correct in round 1, that's a 2 upon 6 chance times 1 upon 5. That's this first one, and we've already seen that. Plus, what about this one? Correct in round 1, so that's 2 upon 6. Then he's incorrect in round 2, so that means there's a 4 upon 5 chance of that happening, and then a 1 upon 4 chance of being correct in round 3, and that comes out to be 2 upon 15. So part 2, find the probability that the contestant selects the correct key in the first round, given that he wins the first prize. So this is the probability of correct in round 1, given that he wins the prize. So that's going to be the probability of correct in round 1 and wins divided by the probability that he wins. So what's that going to be? Well, I just found out that part on top. That's just going to be 2 upon 15 divided by the chance that he wins. So how can he win? Well, he can win by winning in the second round, so there's a 1 over 15 chance of that happening. Or he can win in the third round, so that's the 2 over 6 times 4 over 5 times 1 over 4, which also just happens to come out to be 1 over 15. Or what? There's a chance that he didn't get it correct in the first round. So this would be 4 upon 6, and then he got it right in the second round, so that's 2 upon 5, and then right in the third round, which is 1 upon 4. So this is the other possibility. That comes out to be 2 upon 15 divided by 3 upon 15, so that comes out to become 2 over 3. The variety show runs for 5 days a week over a period of 60 weeks. Find the probability that the mean number of shows per week for which the grand prize is 1 in the second round is more than 0.4. So again, this is a slightly different kettle of fish, so let's get a fresh page. Let x be the random variable denoting the number of shows in a week out of 5 for which the grand prize is 1 in the second round. Right. So what can we say about x? Well, we can say that x is binomially distributed. There's 5 chances for this to happen each week and a 1 upon 15 chance of it happening. So, what does that mean? That means I'm asked for the probability that the mean number of shows per week for which the grand prize is 1 in the second round is more than 0.4. So I want to know a little bit about x bar. Well, this is over a period of 60 weeks, so I've got a large sample of these. That means that by the central limit theorem, my x bar should be normally distributed with a mean of n times p. So that should be 1 over 5 over 15, or 1 over 3, and a variance of npq. So 5 times 1 over 15 times 14 over 15, that turns out to be 7 divided by 1350. This is approximately true by the CLT because n equals to 60, bigger than or equal to 50, is large. Okay? So, what does that mean? Well, the required probability, what we're asked to find is the probability that the mean number of shows is bigger than 0.4. So again, we can do this on our GC, given that we have these numbers, and that comes out to be 0.17723 SF. Okay? Please be very careful that you are very clear with your statement by the approximately by the central limit theorem. So make it clear that you are using the CLT approximation.